So let's say we've set up a study, we've operationalized how we'll measure our variables, and now we're sitting down to run the statistics. It might be a little confusing trying to decide which statistical test applies to our data. In order to know that, we have to think about the kind of value that a variable was able to take in our study. So in practice, a variable can be measured on one of four scales, what we're going to call the nominal scale, ordinal scale, interval scale, or ratio scale. Like when I recorded values for my variable, was I writing things down as a category, like for shirt color or for gender identity? Or when I recorded values for my variable, was I writing it down in a full-on numerical way where, someone with double the number value assigned has double the thing that I'm measuring with that variable? It's important to understand what we are considering here with these four scales of measurement is what you actually write down for each person in your sample, the way you operationalize things. Regardless of whether the construct, the variable itself, could be thought of as a continuous number kind of thing, or a discrete number kind of thing, or something that's inherently categorical. As I've said before, this is going to matter because the scale you use determines the type of statistics you can do on that data and the conclusions you can make. So two people could study the same variable in their study, like, say, age. But if one person is writing age down as number of years alive, right, they're recording it as a number, and the other person is writing age down by categorizing people as child, adult, or elderly into those three categories, then they're going to do different statistics in those two studies, even though they're both measuring the same construct, the same variable, age. So let's go through all four ways of measuring a variable, all four of the scales of measurement in turn. So the nominal scale. Nominal means we're recording things as categories. We are looking at it as qualitative differences, basically, not quantitative differences. So common examples would be gender categories, like if we record gender as female, male, or INB, or hair color categories like blonde, brunette, redhead, black, bald, other, or recording careers like teacher, astronaut, etc. Note here that the nominal scale of measurement means we're dealing with unordered categories. So the values that things could take, we could put those in any order. We could list male, then female, or female, then non-binary, then male. The order doesn't really matter. Any order is just as valid, right? It's not like male is a higher amount of gender than female. On the other hand, some things we record in a way that's more of an ordered category, a sort of rank ordering among the values, like the values just naturally have an order to them. We call that the ordinal scale of measurement. So for example, if I'm comparing whether people's pupils constrict more when they're completing difficult tasks, I have to decide how to operationalize the variable difficulty of task. If I'm sorting people into, say, easy, medium, and hard level of difficulty, those are categories, right? They're not numbers there. It's not a number of difficulty, not 5 difficulty versus 12 difficulty, just easy, medium, and hard. And then I, go and measure their pupil diameter or something. That difficulty of task variable, it's measured on an ordinal scale. Easy is in fact less of that thing I'm measuring than hard. And medium is more of that thing than easy. So there's an inherent ordering to those three values. Or in a survey, if we have someone circle their level of highest education completed, and the options are things like no high school, graduate high school, some college, associate's degree, bachelor's, master's, doctorate, then those values that people are choosing from, they definitely have an order to them. Having no high school is certainly less education than having a bachelor's degree. And a doctorate is more education than a master's. There's an inherent ordering to the answer choices, to the values that the variable can take. So this way of measuring it, we would say, is on an ordinal scale. Likewise for the order of finishing in a race. If someone's classified their value as first place, someone else their value is 7th place, someone else their value is 3rd place, right? There's an inherent ordering to those values. Now, an important note here is that, yes, there's inherently an order among the categories, but that doesn't necessarily mean an equal difference between each step up. Like the difference between no high school and a high school degree, how much educational difference is that? It's not exactly the same as the difference between a master's and a doctorate. Or likewise in a race, if I'm recording what place someone finished in, I'm writing it down as first place, second place, eighth place, fourth place, whatever, that has an inherent ordering. First place definitely crossed the line before third did, but the time difference between first place and second place may not be equal to the time difference between second and third, or between third and fourth. Like, maybe first place and second place were neck and neck, but then third place and fourth place were minutes apart. Now, just a quick side note here, these scales of measurement don't necessarily capture the full reality of a construct. So instead of describing the way we recorded values in our study, right, this is instead just sort of describing the way we recorded values in our study. So like I said earlier, one way of recording gender would be on the nominal scale, putting everyone in a category like male, female, or non-binary. But what if you think gender is more fluid and you want to measure it that way? It's kind of more of a spectrum. If you think a person can be more female or less female, that you could rank people from more female to like most female to least female, if that's what you did in your study, if you've measured it in that way, then you've measured it on the ordinal scale. And note that at this point, we haven't put a number to it or anything. We haven't said Jane is 72 units of female and Maria is 81 units of female. But lots of variables are more like that, where assigning a number, makes the most sense. So let's go beyond ordinal, maybe to the next scale of measurement, what we call the interval scale. In this case, we're going to record scores, and we're going to do it on a scale where the possible scores are not just in order, but with actual numbers to them. And the numbers in the scale here are then going to be in equal intervals. It's going to be an actual number line. In other words, each step up is the same amount. So for example, possible SAT scores range from 400 to 1600. So in a study, I might write down someone's SAT score. That's one of my variables, right? Maybe I want to see if it correlates with something else about them, like the median salary of the zip code they were raised in. Does that correlate with the SAT score they got? Note that the way SAT scores are assigned, the difference between 600 and 700 is the same as the difference between 900 and 1000, or between 300 and 400. Basically, I guess there's no 400, but 300 to 400 on a given subset. So basically, for variables recorded on the interval scale, the steps are equal. Another common example would be temperature in Fahrenheit. Like, think about the difference between 80 degrees and 90 degrees. That's the same as the difference between 90 degrees and 100 degrees. An increase of 1 degree always means the same thing on the Fahrenheit scale. So it's an interval scale. For that matter, though, we could take something most people consider categorical, and maybe in our study, we recorded on the interval scale. Like if we measure hair color, right, as not just categories, but an actual hue using a number that goes in equal steps, not just a category, maybe that could be interval scale then. Finally, the fourth scale of measurement is the ratio scale. This is a special type of interval scale that also has an absolute 0 point on the scale. So it's the type of thing where it makes sense for there to be literally 0 of something. Not just a label of 0, but an absence of that thing. So if we're talking about like duration of time, like we're counting how many seconds it takes each participant to solve a Rubik's Cube, we're going to write things down on a ratio scale, because duration of time has a 0 point on the scale. Or height, length, things like that are measured with a ruler, or weight on a scale. These things are all numbers, yeah, and they're equally spaced numbers, just like on an interval scale, but also they have an absolute 0 point. The ruler starts at 0 height. The scale starts at 0 weight. Likewise, if we're doing a survey where we ask participants to tell us, the number of times something has happened, or where we're observing behaviors and we count how many times it happens, you can count how often something has happened, how many times something's happened. You count up from 0, meaning, 0, never, it hasn't happened yet. So again, something like that would be, there's an absolute 0 point there, we would classify it as the ratio scale of measurement. Now we call it a ratio scale because you can make a ratio between someone's value and someone else's value. Like, it makes sense to compare them as a ratio, or for that matter, as a fraction of one another. So for example, if the first person makes $50K a year and the second person makes $25K a year, we can validly say that the first person makes twice as much. There's a ratio of 2 to 1 in their salaries. So measuring yearly salary in dollars is measuring income on the ratio scale, because you can totally make a ratio between any two people's values. Ditto for age, if we're measuring it in years. If that's how I'm measuring age in my study, if child 1 their value is 10, right? They're 10 years old. Child 2, their value is 15. We can totally say that child 2 has been alive 1.5 times as long as child 1. We can make a ratio between those values, and it makes perfect sense for the kinds of things measured on a ratio scale. Now, compare that to something on an interval scale. There, it makes no sense to give ratios between values. So let's say, for example, Jose got 700 on his verbal SAT, and Sally got 350 on her verbal SAT. Since verbal SAT goes from 200 to 800, there isn't a true zero score. There's no absolute zero value. So it would actually be wrong to say that Jose got twice as much score as Sally. Or likewise for temperatures. Like, if we're measuring temperatures in, say, Celsius, that's a scale, right? It's not a ratio scale, and here's why. We might write down, 10 degrees Celsius for the morning temperature. That's the morning value, 10. And we write down 20 for the afternoon value because it was 20 Celsius. Does that mean the afternoon had twice as much temperature? Like, could we actually make a ratio like that, saying the morning had half the temperature that the afternoon did because 10 is half of 20? That doesn't make sense because we're literally talking about 50 degrees Fahrenheit in the morning versus 68 degrees Fahrenheit in the afternoon. No one's going to describe that as objectively half the temperature. So even though the number 20 is double the number 10, when we're measuring temperature in Celsius or in Fahrenheit, 20 is not twice as much as 10. Like, yeah, we're assigning numbers, and they're kind of equally distant from each other, but in this special interval scale kind of way, not in a ratio scale. There's no absolute zero here. Now, just a side note, before any physics majors try to call me out, yes, if you record temperature in Kelvin, that is actually on the ratio scale because Kelvin, as a way of measuring temperature, does go down to absolute zero. There's a true 0 point, so in that case, 100 degrees Kelvin is literally twice as hot as 50 Kelvin. Or 400 Kelvin is actually half of 800 Kelvin, but only because that's on a scale with a true 0. So it's ratio. So just to test yourself, you might pause this video for a second and decide what scale of measurement is depicted here. In this case, recording the order of finishing for a race would be ordinal scale. A nice mnemonic is kind of right there in the name, ord. So ordered values are required for the ordinal scale. In another study, maybe we compare the reactions of people to peppers of different heat as measured in what's called Scoville heat units. So some things have no heat, some things have a huge amount. You can see it goes all the way down to 0. Pause and consider what kind of scale of measurement this would be. And here it would be ratio. 8,000 Scoville units then is twice as much as 4,000. And again, we know that because there is a true 0 here. Now, what about a survey where we ask people who they're voting for in the primaries for the next election? Maybe we want to see if that predicts the square footage of their home or correlates with whether they're religious or something like that. When we're asking who they're voting for, what scale of measurement are we using? And this one would be nominal. It's a purely categorical thing. There's no inherent ordering to the values. Let's try a few more just to test yourself. So say we're testing if there's a relationship between someone's college major and their expected income in life. The numbers here, by the way, are totally made up. I just made these little graphs for fun. But what scale of measurement seems to be used for each of the variables here? Once again, I'd encourage you to pause the video and consider your answer before unpausing. So in this case, the variable major on the x-axis labeled at the bottom here, that would be nominal. It's a pure category. English isn't more of a major than sociology, right? They're just categories. Income, though, that's a variable, the one on the y-axis along the left here. That's the kind of thing that has a genuine 0 point. Making no money per year is a 0 income thing. So that's a ratio scale. Just a reminder, by the way, of the terminology. The bottom axis of a graph, we call that the x-axis, and the left side, the up and down axis along the left, that's called the y-axis. So if I use those terms, that's what I'm talking about. Okay, now what about this example? What are the variables here and what are their scale of measurement for them? So pause and try that before moving on. Okay, on the x-axis at the bottom, that's education level. And what's the scale of measurement for that one? Well, it definitely has an order to it, so it's ordinal, right? It's ordered categories. Like, it would be weird to put those parts of the graph in different order. If you had undergrad on the far right and maybe no high school is in the middle, and maybe that's right next to doctorate, like that wouldn't really make sense, right? How about the other variable here, the one on the y-axis? Well, that's expected income. Again, right, we saw that a minute ago. So just like before, it's the kind of thing that's recorded on a ratio scale. Someone making 40K is indeed making twice as much as someone making 20K. Someone can make half as much as someone else on that variable. We can make a ratio between them. Now, I do want to point out something important here, which is not to be confused. Don't get confused by the fact that each of these bars gets higher in the example I've shown here in this particular data. I just made up these numbers. Again, it's totally fake. But the numbers could have come out differently, and it still would be an ordinal variable. So the scale of the variable has nothing to do with how your results turned out. The scale of a variable is based on the way you're measuring a thing. So the ordering, the thing that makes educational level ordinal, is in those category labels themselves, even before I collect the data. So even if the data happen to look like this other hypothetical made-up example on the right, where people with graduate education actually make less, in that case we would still say it's an ordinal variable because there's still a ranking and ordering innate to those categories, to those values that it takes. Okay. What about this graph? Look closely at the scale here, since now it's labeled on the y-axis from 20 up to 100. So what's the scale of measurement for income in this case? Now you might have been tempted to say, oh, it's now interval scale since you don't see a zero value, but that's not quite right. Income measured in dollars is still a ratio kind of thing. Someone can still have twice as much income as someone else, and that makes sense. So in this case, the graph's label, just visually the graph's label might start at 20, but income in dollars, the type of thing we're measuring, is indeed a variable that starts at 0. Even if none of the people in our study, even if none of the groups in our study had an average less than 40K or whatever, the idea of 10K income or 1K income or even 0 income makes perfect sense. It's the type of thing with a true 0 on the scale, so it is ratio. Now, this is just a handy reminder in general because ignore the numbers on these two examples here and just compare these two graphs visually, like at a glance. Just look back and forth at a glance between these two. If you just took a quick glance, or if I had hidden the y-axis, you might come to a conclusion that would be very different if you saw one of these graphs rather than the other. But if you look closely, both of them are showing the exact same data, the same results in both of these graphs. It's just a different presentation where they set the labels of the y-axis differently. Like in both cases, psych is 60,000, computer science is 90K, history is 40K. In both cases, then, computer science expects 50% more income on average. Again, these are just made up numbers. But in the one on the right, look at it visually. The one on the right, it looks like computer science makes many times more than history, when in reality, it's barely more than double. But if one of these graphs showed up on, a report on your favorite cable news channel, or if it showed up on the cable news channel that you hate the most, you might be drawn to a particular conclusion just based on the graph's y-axis that they chose to use for the exact same data. So you actually see this all the time on TV, talking head type of opinion, quote unquote, news shows. Like this old example talking about tax rates. Look at the bar on the left here. It's for a 35% top marginal tax rate. And the bar on the right is for, just 39.6% top marginal tax rate. So that's an increase of just a few more percent, but visually the bars show a mammoth difference that at a glance gives viewers the wrong impression that the top tax rate is skyrocketing to something like 5 times as high, just visually comparing those bars. So beware of how information is shown visually and look at the actual labels and think about what the variables are. And is this the kind of thing that actually goes down to 0? Well, then you might need to imagine those bars going all the way down to 0. Okay, let's try one more example on the scales of measurement stuff. What if we tested whether there's a relationship between, the color of the shirt that you're wearing on SAT test day and the SAT score that you got? pause and identify the scales of measurement used here. Well, first, for shirt color, we're looking at a nominal scale because it's just a pure category thing. Like plaid isn't more of a shirt color than blue or polka dots. And then what about SAT scores? Well, as we already discussed, that's interval because the range of possible scores doesn't go down to 0. So we can't meaningfully say anyone got a score that's half of someone else's without being misleading. Now, one final point I'd like to make in this video about scales of measurement. Nominal or ordinal, they are the only way we can really choose to measure a variable that at its heart is truly categorical, right? Meaning a thing that doesn't naturally come in numbers. On the other hand, though, for things that do make sense as numbers, we could still, for our study, choose to measure them in a way that's lumped into categories. Like, we can choose to measure something on the nominal or ordinal scale in my study, even if the construct itself is the kind of thing that would make perfect sense as a discrete number or a continuous number even. So for example, let's make some comparisons of two different ways you could choose to measure and record the exact same variable in a study. So age, for example. How much time someone has been alive. Time is inherently numerical and it has a real 0 point. And age can be, broken down to the level of seconds or milliseconds or below. So it's kind of innately a continuous number sort of thing. That's what age is. But in my study, I may not actually measure age down to the millisecond. Maybe I might ask someone their age in years. And I write it down. I record it by rounding to the nearest year, whatever they said, and report the whole number. That's on the ratio scale, right? It still has a 0 point, and I'm still applying a number to it, and those numbers are equidistant. Like 67 is 2 years away from 69, and 47 is 2 years away from 49, and 22 is 2 years away from 24, right? Equal steps. But in a different study that's looking at age, someone might measure age in a different way. They might do it by categorizing each participant as either young or old. Or maybe they have 3 categories, like young, middle-aged, and elderly. Either way, that is ordinal scale of measurement. One of those is more old than the other, right? There's an ordering to it, but they're just categories. Now, in this case, these two studies, both are studying the same variable, age, but different studies might operationalize it using different scales of measurement. And that'll change how they do the statistics. They'll use a different statistic on it then. All right, what about something like height? Again, this is sort of a naturally continuous number sort of thing, but in one study, I might measure participants' height, to the nearest millimeter on a ruler and record that number, which would be ratio scale. But in a different study, I might just record everyone's height as a categorical tall or short value. And if that's true, then it would be ordinal, right? There's an ordering there. Tall is more height than short. So it's ordinal, but it's categories. Now that doesn't mean that height in reality is something that can't be broken down with numbers, but in my study, I might be treating it as categories. Likewise for number of pets as a variable. Number of pets is something you can just count in whole numbers, right? In reality, you can't really have half of a pig as a pet. So it's what we might call a discrete number sort of thing, not continuous number, just innately. So in my study, it might make sense to record that variable on the ratio scale. I could just count the pets that someone has and write it down as a number. 3, 7, 1, 0, whatever. That's simple. But someone else in a different study might be studying pet ownership in, psychology study where they want to know, they want to think about it in a categorical way. Maybe even a fully nominal scale, like whether someone has pets, yes or no. Or whether someone has enough pets to qualify as a crazy cat person or crazy horse person or whatever, or not. That could be nominal. That could just be lumping people into categories. So we can always choose to take something that's inherently numerical and in our study just record it as categories. And if that's so, then we're going to do the statistics that apply to things recorded as categories. All right, let's stop there for the scales of measurement. In the next video, we're going to think about how to judge whether the way we operationalize a variable in our study is really capturing what we want it to. Basically, how to tell if our operational definition of something applies scores in a way that's consistent and just whether it's a great or shitty way of getting at the construct we're trying to get at.